Hello, this is Vedant Rai, SAP ID 60001180061 from B4 batch of TE Electronics. Today I will be presenting experiment number 3 of my DLIC practicals. The aim of this practical is to design an integrator using OpAmp OP07, and we will also study its frequency response. We are using LT-Spice software. We already know what an integrator is. An integrator is a circuit which produces output voltage directly proportional to the area under the waveform. This is the general circuit of an integrator using an op-amp. We'll see how to design the circuit. We first need our op-amp OP07. Then we need our resistors, control R, resistor 1, resistor 2. Then we need our capacitor, control R, place it here. Then we need a voltage source, one voltage source here and two here for VCC and VEE. I'll connect the circuit using the wire, this line. I'll first connect the VCCB. I'll now label the VCC and VE. I'll right click here and do label net. This is the VCC. Put VCC here. VCC will also be here. This will be VE. This will also be VE. I'll ground the open parts of the circuit now. I'll label V out. So the circuit is ready. I just need to put in the values. VCC and VE as usual, we'll take it as 15 volts. 15 volts. We've performed the calculations to find the values of the resistors and the capacitors. FA and FP have been given to us in the problem. Using the formula, we assume that CF is equal to 10 nanofarads. So using the formula FA is equal to 1 upon 2 pi RF CF, we can find the value of RF, which comes approximately to 15 kilo ohms. And then using the formula FB is equal to 1 upon 2 pi R1 CF, we can find the value of R1, which comes out to be 1.5 kilo ohms. ROM is also equal to 1.5 kilo ohms, but we do not need to use the ROM, the offset minimizing resistor, in this case, because in LT-Spice we have an ideal OP07. I'll now enter the values. We are going to be finding the frequency response. So I'll go to advanced and we'll be giving an AC supply. I do OK. Now I'm ready to run it. So I go to simulate and I do run. I need to go to AC analysis because we are performing an AC sweep. The type of sweep is a decade sweep. We'll take 1000 points per decade and we'll start from 1 Hertz and stop at 100 kilohertz. Okay, click on the output. The upper wave which you can see is the frequency response, while the lower one is the phase response. If I right click here and I don't plot phase, then we get only the frequency response. As you can see, the frequency response remains constant. The gain is 20 decibels until almost 100 or 2 between 100 and 200 hertz, and then it starts to drop. When it meets the 0 decibel line, we get our FB, which is around 10 kilohertz. So that's what we wanted, and we can see we do OK and we hide the magnitude. Then we get this is the phase response. We'll now see what happens when we give a sine wave input to the integrator. This is the circuit. We get 0, 1 volt, 1 kilowatt. So I'll just run this. I click on the input and the output, and you can very clearly see that the input is a sine wave, but the integral of sine is minus cos, so we get a negative cosine wave as the output. Now we'll see a square wave. This is the thing. These are the values I've used. You need to go to pulse instead of sine. And I do OK, simulate and run. In clicking on the input and the output, and you can see for a square wave I get spikes of alternate peaks. Then finally I'll see the triangular wave. Now these are the values I've taken, and I go to simulate and run. Click on the input and the output, and this is the integral. This is the exact output that we were expecting. So the integrator is working perfectly. That's all for this experiment. Thank you.